Yeah, not so good as well.
What was in it? What,
So it had a lot of, see, I don't know, because I can't remember exactly what was on there, and I don't have I guess the exam. I won't get that until
okay.
probably next week.
Was it like fairly actually like what was it topics that you saw and the same, or was it something super hard?
Well, just, it was most likely things that were already covered, but it was just, I just I couldn't follow it.
Okay.
Um,
We'll talk about it. So it's usually because of these two exams in the same week that makes it like quite difficult. And
yeah.
we'll see. Like it won't be that bad. I don't think. I think maybe he'll curve it. But I think we need to focus on like this one. I think this one has like a lot of bearing on it for like the differential equations.
Uh-huh.
Did you get a chance to do some of the problems now?
Well, that was my plan, but the
Yeah.
problem was that today we ended up getting car trouble, and
Oh my
we
goodness. Oh, so
had
sorry.
this week's already bad enough, and
I
so
know, right?
basically this we ended up having to, like, our car ended up being under a one of the, I guess it wasn't like a defect, but it was, I guess, a recall.
Oh,
And so
there was a recall.
yeah,
Okay.
and so we had to bring the car in for service, and
And
get
then that
that
kind of took away
fixed.
time. Took away some time.
Yeah. And
I see. Oh my goodness.
then I was planning on, because I had some of my, it's like homework for the other class that's due tonight, and
Yeah.
I'm on the last two questions. Um
Okay.
and then that's for math methods. It's basically for matrices, find
Okay.
transposing the matrix, finding the inverse, complex conjugate, and
Okay.
transpose conjugate.
For which class is this? This class?
This is mathematical methods, which is
Oh, that's for
math.
another class.
Yeah, mathematical methods in the physical sciences.
Oh,
It's
okay.
a pretty interesting class. It's kind of like an all-in-one type thing. Like they go over little
All
bits
in
of
one.
everything.
Those are fun.
Yeah, so this is basically the linear algebra section. And so
That's
I
good.
have,
Linear algebra is fun. Good thing you're
yeah.
taking that class. Yeah.
And so I have this to do tonight, as well as the um, lab as well.
Yeah.
The post
It's
lab
like all
reports due.
it's like everything is just going like piling up. And I
Yeah.
understand. Let's well we have today, and then we also have tomorrow.
Yeah. And
So
I mean, for sure, tomorrow I have time to actually work on it, before the exam on that, like in the evening.
yeah.
But
Oh,
it's
it's in the evening. Okay, that's good. Yeah. I feel like maybe let's cover like maybe some of those questions you had
okay.
first. Can you give me like today was really like every second was like in after the another. I haven't gotten a break yet. Do you mind maybe like 2 minutes?
Sure.
Okay, hold up. Let me just pause this.
Yeah, you want me to come back around 12?
It's no, no,
Or
it's fine. It's
okay,
fine. Just give me like 2 minutes.
sure.
Okay. All right, I'm back.
Alrighty.
All right, let me see. All right, so I think I remember. I think it'll be good actually to talk about like these. Did you get my email about these guys?
Yeah, the kind of lingering questions.
Yeah. So like some of these are just like really knowing how to classify them,
Right.
and then like, if you have them, like these types of equations, then there's a specific algorithm that you have to use to solve the problem. So like we talked about like linear and nonlinear, right? Versus nonlinear,
hmm
and then that's just like if you have what's the difference between those two? What's a linear? Do you remember?
Linear is basically it's just I guess, you just have it's like the prime, it's like I'm trying to think, like you separate each of the differentiable terms, from each other.
Okay. Okay.
And so it's like, for example, 2i, or I mean, not 2i, but 2x second derivative, plus 5x single derivative plus some x, and then, you know, plus, and then a number equals 0.
Okay. Okay.
And
So
there's nothing like two variables multiplied by each other and one of the variables is a derivative or anything. It's just all separate from each other.
okay, kind of. Just remember that linear means that your your dependent variables. So in your case, like, it's x is your dependent one, right?
Mhm.
Right.
Yeah.
So like this, your dependent variable. If all you have to check for linear is if your dependent variables are not raised to a 2 plus power.
Yeah.
If they're not raised to a 2 plus power, that means they're linear.
Right.
And then also, yeah, the other thing is if there's no transcendental function, or like there's no, all these other functions, exponential and trig.
Yeah.
If your dependent variable is not operated by them. So if they're not, then it's linear. If they are, it's linear. So
Got
linear
it.
is if it's being raised to 2 plus power, or when your dependent variable is inside a transcendental function.
hmm
That's it. That's all you have to remember. And then what about homogeneous and inhomogeneous?
So homogeneous, is basically you have your left and your right hand side, and you have whatever your left hand side can be equal to 0 is homogeneous, and then non-homogeneous would be if you would get a non-zero answer.
Okay, so left hand side does not equal 0,
Yeah, that would be
or
inhomogeneous.
or when you have a right hand side.
Yeah, just whatever side has a 0, I guess, or the
So
other side would have to be equal to it to be
yeah,
homogeneous.
so homogeneous means it's equal 0. Inhomogeneous is this it's not equal 0. There's a
hmm
number there, some expression. Okay, that's an easy one. So then there's other ones though. So this first one is what is an integrable equation? So an
Okay.
integrable equation, this is one of those classification ones. And
hmm
then just extend it, maybe like let's solve it. So a form of I call it IE, the integrable equation, standard form. This is the standard form. You have like a y prime that's equal some function of x, the independent variable. So y
Okay.
prime is the dependent variable that's being raised to some like I think first order in this case. I think you could probably do a second order as well, but some degree of like differential, and then the right hand side is a function of the independent variable. Does that make sense? You just have to look at this and then see, okay, if there's a form in there that looks like this guy, this is an integrable equation.
Yeah.
Okay, so let's try, and then we'll talk about the other ones like sequentially. But for this one example I have is because I think you may have to like do some of these, like solve them.
hmm
This is kind of like a specific example. What if you had like an x squared times a y prime equals some number. So first of all, this guy is not in standard form, right?
Yeah.
So what you have to do, for the most part, it won't be. If it is, it's super easy to classify. But if it isn't, you have to convert it. You have to convert the differential equation to an IE, or like an integrable equation. It's easy. What do you do here to make this happen?
So to get the y prime, you would just divide both sides by x squared.
Yeah. So divide both sides by x squared, and then
Mm-hmm.
you get this form, right? You get a y prime equals -1 over x squared. And then so you kind of assess it. Is this kind of like this form? Is this kind of like what we have here? It is, right?
Yes.
So this is in fact integrable. This is an IE. This is an IE.
Mm-hmm.
And I would just like, have that kind of criteria in your mind, saying y prime equals some function of x. Not a function of y, not times a function of y, just a function of x. And then we're going to talk about, the other ones. And this one is like what it is. If it's not this, then it's not integrable. Okay. And then so let's try solve an integrable equation. Let's do an IVP. So an IVP here, you have your differential integrable equation. You have your initial condition. Give me the particular solution. So if it's already okay, if it's already a standard form, you don't have to do this first part. But if it's not, do the first part, and then the second step would be let's find the general solution to the differential equation. So in something like this, y prime equals f of x, what would be like the logical thought or like a step of like trying to figure out what y of x is? What would you do?
So I mean, it's a y prime, and if we want a y, we would integrate it.
Yeah, so pretty logical. Why don't
So
we just integrate directly? So that's what I did. You just integrate. You isolate the y, make it. Obviously, you could technically do the same thing as with a separable.
mm-hmm.
Just do integrable both sides. This becomes y, and then you have to evaluate the right hand side. So all the integration rules, just simplify it to make life easier. So you can just do a chain rule,
Mm-hmm.
reverse chain rule. So after you do all the calculus, you get this, and make sure you get like a constant of integration, right? Because this is a indefinite integral. So you get one constant of integration. And that makes sense why you would have one constant of integration, because this is, with any differential equation, the number of integration, or the constants that you have to solve for, is the degree of the what?
Degree of the, I guess, of your dependent variable.
Yeah. So the degree of the dependent variable is the same as the number of differential constants you have to solve for your particular solution. So this is your general solution. This is your general solution. It's general because you have a constant and you haven't
Mm-hmm.
applied your initial condition. The last step is find the particular solution to the differential equation by applying the initial condition, right?
Yes.
So initial condition, since it's only one degree, one differential, first order of differential equation, you only need one initial condition. So this is what I have. And then so we just plug in what we have. So that's 3, right? And then you plug in 1 for x. So 1 over 1 plus c1. And then you do your steps. You find that c1 equals 2, and then that's it. It's pretty simple. Does that one make sense?
Yeah. So basically, we're given the initial condition, and then after we integrate it, we then just plug and
Chug it.
play. Yeah.
Yeah,
Okay.
pretty much. It's really simple. That's why it's like directly. Another name for this is directly integrable, because
Okay.
you can just definitely do the integral directly. You don't have to do any like approximation stuff. Okay, but the one thing to remember is this is the form. The form is this. It's not times anything. It's this form. This can be any number. but as long as the right-hand side is only a function of the independent, not the
Mhm.
dependent. Okay, let's move on. So the reason why I say that, like, remember the form, is because, do you remember separable equations?
Separable equations, yeah, you can have each side be a different with respect to a different variable.
Yeah. So, and that is a look of it. I would just remember this form. What I have here, y prime equals f of x times gy. So another function, but it's a function of the dependent.
Right.
So if you look at this guy, it looks kind of similar, right? It's kind
Hmm.
of similar, right? But the only difference is it's being times by the dependent variable now, by the function of it, a function of it.
Yeah. I
So when you
mean,
see, yeah,
it's a y prime, so couldn't you just bring over the g of y over so that each side,
you
one
could.
side is with respect to x and with one side with respect to y?
Thus, yeah, that's the reason why it's called separable, right?
Right. Okay.
That's the reason why it's called separable, because you could do that. But essentially, that's the form of it. This is the form that when you have something like that, where the right hand side is not fully one function, then it's called separable. In essence, you could call this separable, like an integrable.
Yes.
But
Separable, integrable.
yeah, so in essence, this is like a separable as well. But at the same time, a separable one is one where you have, this form. When you have this form, that's what you have. Okay. And in this one, you're probably more familiar with this one because we've seen this so many times. But let's just try like breeze through it. So you have this example. You have y prime equals a function of x and a function of y squared. And then like let's try to assess this. Is this linear first or is this non-linear?
It would be nonlinear,
Why?
because of the squared.
Yes, because this is the squared, which is not one. If it
Okay.
was one, then it would be linear. Hence the definition of linear. Okay, so you have that, and then now you also have initial condition. This is going to be an IVP, kind of similar. I just wanted to do this so that you have like the full set of like what it is and then how you solve for it.
Okay. So it's an initial value product problem because they give you an initial condition.
Yes. If
Okay.
it if it's not initial value, if there's no initial condition. Another
Okay.
one would be a
Boundary
boundary value.
value.
A boundary value just means it's a space condition.
Okay. Is there really a difference or is it just with multiple dimensions?
Once you get to multivariate space and time, then it's called PDEs now. And for a
Okay.
PDE, not what we're working on with now is an ODE.
Hmm.
With a PDE, you're going to have a boundary condition and an initial condition. You're going to have both of these guys.
Okay.
But
Yeah.
right now,
Which I mean, it's just double the work.
it's double the work and like crazy algorithms. It's fun, but it's kind of crazy.
Okay. So,
Okay.
I mean, is there really a difference in terms of how you solve an initial value versus a boundary value?
For ODE, no. Like in
Okay.
terms of because like this initial condition, you're just plugging them in boundary condition. You're just plugging this in the general equation, right?
Yeah.
You're plugging this in so that you get a particular solution. That process is the same, either if it's PDE or ODE, is the same. The only difference is getting the general solution. So the general
Right.
solution is different. But right now I don't know if I think you guys will probably move on to Laplace transforms next, right?
Probably, yeah.
Because like right now, you know how like we have all these different algorithms. I mean, they're really all over the place. There's no uniformity. But and then there's like different steps for each one. Once you like I think the next one Laplace transforms, this one will kind of unify the rules. It doesn't matter what you give it, first order, second order, non-homogeneous, homogeneous. You can solve for it, and it's just one method. Okay, so for this one, let's solve the general solution. Get the general solution of the differential equation. So like for the most part, when you try to do like a separable equation, when you have like y prime, I
Hmm.
usually do it this way. I write it like this.
Mm. Okay.
The reason why is so that you can separate them, right?
Yeah. Okay. And I mean, a question I kind of have is with how you write y prime as dy dx. Why is
Okay.
it that when you have the second derivative, it becomes d squared y dx squared? Why is the squared in a different position?
Okay. I mean, that's a fair question. So when you look at this guy, like this is just an operator.
Okay.
Yeah, this whole thing right here is an operator.
Oh,
And,
okay.
yeah, d squared over dx squared, and then this whole thing operates on y,
Hmm.
right? And then so like this dx, so you have dx or d dx, and then dx, right, on the bottom right here, right? This dx is just
Yes, I
dx
guess, yeah,
times
because you do
dx.
it twice.
You take the
Okay,
differential with respect to x twice.
got it.
Yeah.
Okay.
Okay. So yeah, like when you do dy dx, the reason why you do it, you're separating the y prime into that and making that form is so you can separate them. And then like I think you're pretty good with this one because like I think just the knowing what an integrable is versus this guy, but you know how to do it from here, right?
Yeah, so you would integrate both sides after you bring the you would bring the y squared over. Um,
Yeah.
so you would have
Yep. You
y
integrate this
prime
guy.
over y squared equals x,
Yeah.
and then you would
Y,
integrate both sides.
and then you times and you do some
Okay.
cross multiply. You try to isolate the y, right? You
Mhm.
isolate the y. That's the goal here. Is to after you do the integral on both sides, yeah, you isolate the y, so because that would be your general solution. Does that
Okay.
make sense?
I mean, yeah, how did you get the 1 over y? So did you take anything out?
No, it's this so this guy right here, 1 over y squared dy,
Okay. dy.
and then I did like y negative 2 dy
Okay. Yeah.
plus 1 y negative 1 divided by negative 1.
Hmm.
Yeah, and yeah, that's the same as this guy.
Got it. Okay. That makes
Okay,
sense.
okay. So with that one, and then when you cross multiply, you do this, and then you get this, and then you don't really have, like, where do you put this constant? This plus c1. Where do you put it? Do you put it in the y or the x, right? Like, because like
Yeah.
they're both indefinite integrals, right?
Doesn't matter.
Yeah, it matters. You put this where you plus it where you have your independent one, because that's what you're. It's like you as the mathematician or the physicist or whatever, that you have the choice of where to put that, but then you're solving for the, you want the y of x, right?
Y
So
of
the y,
x.
so
Yeah.
you're gonna solve for this guy, and it's just an arbitrary constant right now. But the best way of doing it is put it where the independent variable is, and that's just the rule. You put it where the independent variable is. You plus it at that side. You don't plus it here, and then like, this one is 0, and then it's going to be minus c1. You just put it where the independent variable is, and you manipulate.
Okay, so
And it
you
just,
always put the c with the independent variable?
yeah, you put it the positive constant in the independent variable, and it,
Okay.
and then you solve for it. You solve
Is
for
it
it. You
with or independent variable or in the independent variable?
uh in the same side, in the same side. You know how like when you have, or not inside the variable, but obviously like in the same right hand side.
Okay, yeah, because like you have the y and the x there on the same side.
Uh, in the beginning, when once you evaluate, once you evaluate the integral.
Yeah, but I mean like near the bottom, you have the 2 equals y times the negative x squared plus c.
Yeah, but then like you got the C1. This is all the manipulation, right? This is all the manipulation. You only get the C1 once you evaluate your integral, right? Right? Like, because this is improper or like indefinite.
Okay.
All these other things I'm doing here is just manipulating so I get a y. It doesn't matter now where your C1 is because you're manipulating it. The only times that it matters, as long the math is going to work as long as when you're putting the C1 is after, because that's the only time it matters, is where do you put it, which improper or which indefinite integral, and it would be for the x. And then you get this guy and then manipulate. After you manipulate, it doesn't matter. There's a y right here. The reason why we're doing that is so that we can isolate it. Okay. So this next part is pretty simple, right? Initial conditions.
Yeah.
Yeah? Okay.
You just plug in what you're given, and then you solve for your C, and then you go back into what you had with the C and replace your answer with where the C was.
Yep.
So that's your particular solution.
Sometimes it's called unique solution. Other times it's called particular, but yeah. Because like sometimes when you say particular, it may be, remember we talked about particular versus complementary?
Yeah.
In that time, during those times when you have to do the inhomogeneous, then you call it unique. Because which one is which? But like if you don't have to do that in the homogeneous case, then it's this guy.
Okay. Well, are there any separable equations that require both solutions?
So the complementary and the particular.
Particular, yeah.
I think in this case, because like in those times when you're only doing like YC and then YP, the reason why you do this is when you have like a non-homogeneous, right?
Yeah. Okay. YC and YP. Okay. And I mean, I know that particular is also known as unique. And I also know that complementary is also known as homogeneous. Since there's two names, is there a situation where instead of, here we found the unique solution, but are there any cases where we only find a homogeneous solution?
Is there only one where you only find the homogeneous? If it's a homogeneous one. If it's inhomogeneous, you find both of them. This is the only time it matters.
Okay, so in this case, this can either be called the particular, the unique, or the homogeneous.
Oh no. Okay, in this case, this is just the reason why it's called particular. That's why I don't like calling it particular, is because a particular solution, the definition of it is when it's like a unique solution to a general solution. It's a general one if you haven't done any initial condition or boundary condition. You haven't applied your initial condition or boundary condition. It becomes particular once you add in your account for the initial or boundary condition. In this case, you don't have a homogeneous because I don't think this is even, you don't actually classify these guys as a homogeneous or inhomogeneous. That's like a different story, which is like what we're talking about, So
we can't tell if this is homogeneous or non-homogeneous?
I don't think so. Like that terminology is mostly for when you have this case. This is called separable, which is different.
Okay, but I mean, this is separable.
Yeah, this is called separable. It's not non-homogeneous or inhomogeneous.
And it's not homogeneous either?
It's not. It's separable.
Got it. Okay.
And I guess if you're talking about linear, non-linear, that one you can classify as non-linear, but not homogeneous or homogeneous or inhomogeneous. Okay. And then that's it. You pretty much solve it the same way as any IVP. This next one is probably the harder one.
Yeah, you're going all the way to the end, yeah. Okay.
Yeah. So the Bernoulli, you've heard of the Bernoulli, but how much did you guys cover on this one? Was it like a few weeks, a few days?
I mean, it was a few days. There really wasn't much that I can really retain or know or remember or recall about it.
Yeah. Okay. Let's just cover it like as if it's new. So Bernoulli standard form. Always remember the standard form. You have the integrable equation y prime equals f of x, which is the integrable, and then separable equation, which is y prime equals f of x times gy, separable. And then the Bernoulli now, is the form that takes this type of equation: y prime plus, and it's a little bit weird, but just go with it. This is, you're gonna see some things when you look at this, they're already defined this way, so it's a little bit easier to see. But you have y prime by itself plus some function of x times like this y, zeroth derivative, and then equals some function of x again. And then this y is raised to like a power n. Somewhat weird, yeah?
Yeah, so it's just
Yeah.
some power.
So this is just a form that it takes, which is called a Bernoulli equation. And if you can write it in this form, well, so maybe sometimes you have a coefficient here, but what if you divide it and then you can write it in this form? Then it's called a Bernoulli. If you can't write it in this form, then you cannot classify it as Bernoulli.
Okay, so I mean, you said you can divide it over, so in that case, what would that, I guess, the divisor or whatever, which was the coefficient, what would that,
probably a number.
what part of this equation would that fit in?
So that would be maybe like a 1. Like, but the equation you're trying to classify, it could be this equation or it can't be this equation. If it's just a coefficient, it's not really a function of anything. So maybe like there's a 1 here, yeah? Or maybe there's a 1 here or 2. But we're not counting for those. What you have to look for are like the variables, the independent and the dependent.
So you just ignore, like, if it was like if there was like a 5y prime,
if it's
and
a
you
5,
could divide it all.
Yeah, if it's a 5y prime, you divide it by 5, and it still will take it will take into a form like this because it's just a constant. It doesn't really change much. If it's a variable, it's gonna change it, and if you divide it by like an x right here, then it's not this form. You don't have this form. If it's a constant, it's okay. All right, but this form is a little weird, not only because it's a standard form, not because of its standard form, but then the way you even solve for it. And the way you solve for it is kind of similar to how you solve for it with a first order differential equation. Do you remember that, the integrating factor?
The integrating factor, yeah, it's some
I'm not covering that today, but yeah, the integrating factor is also used in the Bernoulli equation.
Okay.
So let me just say what that is, because after the very first thing is you ask yourself, is this equation in this form? If it's not, create this form. The reason why is you're gonna need this f of x, and you're gonna need an n to get your integrating factor. And that's just the algorithm. I guess that's when you do this, you have this e, kind of like similar as the integrating factor. You have the integral to the raise to the integral, but this is where it changes. It's not the same as like how it usually is. So you take the integrand as 1 minus n times this f of x. This is the term that's in front of the zeroth derivative of your dependent variable.
Okay.
And then it's dx. So different is different from your regular integrating factor, but this is the Bernoulli form of that. And then your general solution takes into this form. Y 1 minus n, like I said, it's weird, 1 minus n equals, this one right here, you're gonna isolate the y, but this is just the form so that I'm writing right here, but and then you still have to isolate the y. So y to the 1 minus n equals 1 over this integrating factor, all multiplied by this thing right here, the integral of 1 minus n. Now you're going to use g of x, and this is the term in front of your, it's inside, it's in the right hand side, and it's being multiplied to this 1 y to the n, and then you times it again by the integrating factor, and then that's it. That's your integrand, and then you plus c.
Okay. So basically, we have to convert this integrating factor into the next form. So
Yeah, it's a lot of work. This is the one I don't like to do usually. So because of like if you look at it, the form itself looks weird. The integrating
So
factor, yeah.
it's basically, if we were to plug in our I here, of course we would need to determine what our n is and things, but you would end up having the form of y to the 1 minus n power
Yeah,
equals 1 over e to
I
the integrating factor. One.
It's an there's no e here. It's just 1/i.
Well, yeah, but it's like 1 over I, and if I is e to the integral of 1 minus n f of x dx, you would basically put that
Oh, I see
in
what
the
you're saying.
denominator.
Yeah, you could do that. Yeah. Yep. Okay.
And then that would all be multiplied by what's in the parentheses.
Yeah, and then there's also an I here as well.
Yeah, the I dx plus c.
Yeah, I think for the way it's easier to see or like to compute, I would because like the I shows up twice, and it's also you have to take the integral of it.
Okay.
Since you're taking the integral of it, like if you want to just remember one equation, yeah, you could do that, but it's gonna be really hectic because then you're tracking so many things. You have to put this inside the integral.
Yeah, and I don't understand how you got the y to the 1 minus n at the top.
Yeah, it's like I said, this is just the way the algorithm was placed. You have to get it in this form. The reason why you have this form is because you're gonna use these individual variables to create your integrating factor. And then once you get the integrating factor, you have to create your general solution. As I said, this form is just Bernoulli equation is not something I prefer, but it's like one of those like rare occasions. Like okay, you have a Bernoulli equation, so you just have to follow like these steps to get the actual general solution.
Okay.
And there's no rhyme or reason. It's just okay. Like mathematically, maybe you can prove like why this is the case. Let's not cover that. That's like a proof thing, like conceptual stuff. Okay, so just to use it, like let's actually try use what we just talked about. So here's actually a differential equation that you can classify as a Bernoulli. This is a simple one because it's already in that form, the Bernoulli equation form. And if you actually look at problem 11, I think that some of them are Bernoulli. Like you're gonna have this y prime by itself, and then you're gonna have like this y that's like times by some function of x, and then this whole thing is equals some function of x again, g of x, and then this y is raised to this other power, which is n, right? Okay. So you have these guys, and then like I said, let's just put in like an initial condition. So that's like IVP, just so like to complete the set of how to solve for these guys. But like mainly for like a Bernoulli, as I said, the form is really important for a Bernoulli because you have to take all these different parts and then kind of manufacture your solution from that. So once you get it to the form that we talked about here, just get an f of x, g of x, and an n.
Okay, so
Okay.
you just identify.
Yeah, just have after you have the form, you just pretty much identify what they are.
Okay.
So in this case, it's already in this form. If it's not, you have the very first step is create that same form. And so g of x is x squared, n equals 3. That's pretty straightforward, right?
So the y g of x is x squared. Yeah.
It's just reading it from the form. I think the hardest part is like remembering what the forms look.
Yeah.
But like, it's just a recipe. It's a cookbook. Get the parameters. Second step is find the integrating factor. Integrating factor of the different. So what was that? The integrating factor is, what was it? E raised to the same as the integrating factor, but then this one is 1 minus n. 1 minus n, f of x, and then dx. And then you just go along with the math, and then, you got -2. That's 1 minus 3. times it by 2 over x. And then the minus 2 times the 2 is negative 4. That's just a constant, you take it out.
Okay.
And then the only integral you have to evaluate is this 1 over x, right?
Mm-hmm.
And then like, what's the integral of 1 over x?
That's natural log of x.
Yep, that's the one.
Natural log of the absolute value of x.
Yeah, it would be this guy. It could be n of like absolute value.
Mm-hmm.
In this case, let's see. What we could do here is because it's x to the 4th, it's an even power, so we could just do this because this is an even power. If it was like odd, then I think you have to put in the absolute value. Okay.
Yeah.
Anyways, the rule of it, the rule of exponents, you transfer the constant of the power so you can cancel the e and the natural log. And then this is your integrating factor.
Okay.
Does that make sense?
Yeah.
It's just going through the step of that equation. No rhyme or reason. It's like, oh, okay, going through that, and then the general solution again is the third form of it. Is what we just talked about. This plug and chug. You have your n, you have your I, you have your I, you have your g of x, you have your n, and then like you add the c. The c right here is what you're accounting for, because this is a differential equation, right? This is a first order differential equation.
Mm-hmm.
So you have one constant you have to solve for. So you solve for this. 1 minus 3 is 1 to the negative 2. You plug in the I, it's 1 over x to the 4th. So that just turns to x to the 4th. We times this whole thing by the integral of 1 minus 3 times x squared. And the integrating factor is 1 over x to the 4th, d of x plus c. And then with this, just simplify the integral of negative 2, 1 over x squared, d of x plus c. And then you just keep on simplifying x to the 4th, the integral of negative 2. You can, I think it's easier to work with like the negative exponents for the integral. Negative 2, you don't want to do quotient rule here. So x to the 4th minus 2, x to the negative 1 over negative 1, that's the integral, plus c. And then so you simplify this so that you can cancel the x to the 4th. So you put the x at the bottom. And then so, is that your dog?
Yeah, he screams because there's some reason, I don't know why, but we have crazy neighbors. I don't know if they were either
Oh my.
probably firing the
Firecrackers.
firecrackers, I think.
Yeah. Yeah, sometimes it's like that. For me, like, since I don't have a dog, I just have the alarm. So
Yeah.
it's either one. Okay. So with that, like, okay, you cancel out the force of 2 to x cubed, and you have this x, so you have this x, right? This x. Oh no. Come on. Are you serious? Or it does this sometimes. Where were we? Bernoulli? There you go. I thought I got cut off. That was. You gotta redo the whole thing. Okay, so you have this x to the 4th since you distributed this guy.
Okay.
And then so you just simplify. And then like this is kind of similar to the other one. We have this like 1 over y. So why don't we cross multiply or just do the reciprocal? So I just did the reciprocal and I took the square root to isolate the y to make it a general solution. So it's just applying the equations, right?
Yeah, pretty much.
Yeah, there's really, like, for the Bernoulli, just remember like for the separable and integrable, it's really easy to see what they are. But for the Bernoulli, you may have to manipulate the equation.
Okay, so I'll just remember two equations for Bernoulli.
Yeah, you really have to remember this one because like it's not like regular calculus where you just integrate. You have to remember the equation and then do the calculus after you remember it.
Mm-hmm.
Okay, and then again, particular solution for the differential equation, and you get this. Okay, let's move on to the exact equation.
Okay.
What do you remember from this one?
So, so you would kind of have it. It would also be kind of like a thing similar to it being equal to 0 to, or
Yeah,
like equal to something else. But it has partials in it, I think.
yeah, yes, partials. Yeah, you're right. So the form that it takes, I'll just let's go over it. Is this guy right here?
Okay.
This is the standard form. All of them always have a standard form, and that's how you classify them. If you fit the standard form, you're good to go. In this case, there's an extra because you're taking partials, right?
Right.
So this form right here, m partial x, and it's a function of x and y times dx, and then you have n partial y, which is a function of x and y times dy, equals 0. This is usually the form. You have this dx and dy, and then you have some function of x and y that's a coefficient of those guys.
Okay, so like I was just wondering because they always use I find these to be interesting because it's like why do they
Okay.
choose to use M and N?
It's really up to like the inventor, the mathematician, or the physicist.
Okay.
Like maybe the guy was Manuel and like Nick.
Yeah. So it's like
Because
so basically
yeah, go ahead.
like so you have two functions in here.
Yeah.
How do you know that I guess what functions those are?
So general again. So like it's not for the exact equation. It's a more of like a check, not if you can fit the standard form. So like once you see something like this, all you have to look for is some function of like x and y.
Okay.
It doesn't matter what function they are, or some function of x and y. So like usually the ny is the one in front of the dy usually.
Okay.
Because like how you check this is like, well, we're gonna talk about that next. And then the m's partial x is the function in front of the dx. But that's not how you classify it. How you classify if it's an exact equation is the next step. The next step is take the function in front of the dx, take the partial of it in terms of y. So the m that you have, take a partial of y.
Okay. Why would you take it with respect to y when we have M sub x? Wouldn't you take it with respect to x?
No, because you're gonna cancel the x, the dx. That's the rule because this is dx, right?
Right.
And then you take the partial in terms of y,
Okay.
the opposite. And then for the dy, you have to take the opposite, the partial with respect to x. In essence, you could say the m is associated with the dx, and then since m is already like it's already a partial x, you have to take the partial of y.
Okay.
And then for the dy, since it's you can essentially say that's the ny term, the everything in front of the dy. And then since it's already a partial dy, you want to take a partial of x. And then this is the trick here. Once you take the m of x, m partial x, m partial y, and then n partial y, n partial x, and you make them equal each other, or like if you compare them, if they're equal each other, equivalent, if they're equivalent, then it's called an exact equation.
Okay. So do you have to basically take two, basically do a partial derivative of each piece and then from there see if you can equal each
Yeah,
other?
Yeah, but do remember you're only taking partial once. This term in front of the x is already a partial. It's already a partial. You only take a partial of it with respect to the one that it's not supposed to be there. So
Yeah,
for
I
this,
know. I was
okay,
I was just kind
okay,
of
good.
choosing the whole thing. So like you would do two partials, one of them being for m and the other one being for n, and then you
I see what
set
you're
them
saying.
equal to
Yeah,
each other.
yeah, you could do that, and then the other one would go. The thing is with that is like if you take a partial of y of everything, you're gonna have a lingering one. Like this whole thing is gonna be lingering. What I would do is just take the term of like this guy, like subservient them just take them out so that this m of x term, just look at it, take a partial of y, and then look at the term in front of the dy, and then compare it to, so that's the ny term. Take a partial of x. Yeah, take a
I
partial of x.
I don't know. Uh, so
Yeah,
that so it still seems like so do you just take a part of the second one or
yeah. Like I said, this is the way they created the function. And it's like what you do with let's see, f of x, y. What was that one? It's like f of x, or partial f of x with respect to y, and partial f of x with respect to x, right? Something like that. Plus like f of y dy, d of f, d of x, dx, plus like d of f, d of y, dy. And that would be your df, there you go, rather. Df x of y equals that. But I wouldn't remember that way, and then don't try to like, okay, like that's the term there. I would just take the term of like mxy, mx in front of the dx, and then because like all of this, we're not talking about physics here. We're just talking about math. I know, like once we get to like combine the physics and the math, then like, oh, like maybe you can't do that because you're not doing it to the whole equation. But I think it's better to talk about that once we actually have like a word problem. In this case, we're just trying to solve these equations. So just accept that the term in front of the term in front of the dx, just take a partial of dy of y. The term in front of the dy, take a partial of x. And then if they equal each other, then that makes them an exact equation.
it's just dx with respect to y and dy with respect to x?
Yeah, the dy term. Not the dy itself, but the dy term. The term in front of the dy, and then the term in front of the dx.
Okay.
Well, we're gonna do an example which would make more sense. We're not talking about like hand wavy. Okay, so just to make more sense, let's actually give like some values to this. So the m of x, or m partial x, is 2x minus y dx. The dx, and then the n partial y is 2y minus x dy, and this whole thing is equal 0. So if you do this, the very first thing I would do is to check if it's an exact equation. If they give you something like this is kind of like in problem 11, there's some terms like this that look like this. I mean, yes, you could just say that maybe it is an exact equation, but always check. What we're gonna do, what I just said, is you take the m x, take a partial of y. So whatever is the m right here, take a partial of y. So you have that, and then so 2x y partial of that y d dy is 0. Minus y partial of that y d dy is -1, right?
Mhm.
Right? Because
Yes,
because
so
because the 2x is just a constant in this case.
okay, so it's basically we're given the 2x minus y dx.
Yeah.
And then that's plus 2y minus x dy equals
Yep,
0. Okay.
equals 0. Yeah. And then the very first thing is you want to check if this is an exact equation. And then how do you do that?
Okay, so you would basically take the first with the dx, a partial of the 2x minus y with respect to y.
Yep. Another way of writing this is d dy 2x minus y.
Mm-hmm.
I just like writing this sub notation. And then so d dy of 2x minus d dy of y. This one goes to 0, this one goes to 1. So the answer is -1, right?
So this would be 2, this would just be 2 dy minus, I guess it would just be 2 dy.
To which one?
So just for the 2x minus y with respect to y,
Yeah, the 2x is 0, right? Because it's
so
of
you would just
x.
get 2 dy.
There's if you take the value of 2, evaluate this guy minus, isn't it derivative? There's no 2, right?
Yeah, because I thought that when you take a derivative, like for example, with respect to x of 2x, you would
Yeah,
just
it's
get
there.
2. But
You
then
wouldn't get, okay.
since it's
If you
y, since it's dy, you would do the similar way, but instead of writing it with respect to x, you would write it with respect to y. So you would just have 2 dy.
I don't like let's break it down. It's not 2 dy. It's so when you write this guy d dy, right? This is partial, right? Does it make sense to do the partial like this?
Yes.
And then you, because it's just an operator. I want to do the d dy partial of 2x minus y, right?
Right.
And then since it's an operator, you can foil the operator, right? It's just an
Okay.
operator. So d dy 2x, right?
Right.
Minus d dy of y, right?
Mm-hmm.
So what is d dy of 2x?
d dy of 2x, would it just be 0?
Yeah, because it's all constant. There's no
Okay.
y term.
Okay, because for some reason I thought there was a case where if you were doing a partial with respect to y and you had another variable there, you would basically still take the derivative of it, but you would treat it with y instead.
This one. The one that you're talking about is when it's being multiplied. So this is not the case for this one. You're talking about this guy, right?
Okay, yeah.
So when you do this, so let me take the partial with respect to y.
Okay.
So the 2 stays the same, right?
Yeah.
The x is gone because it's not, it's not part of this guy. So it's going to be, yeah. So this case, you don't do that. Like, oh, actually, let me see. When you do the product rule, let me see if you do. I think you do the product rule in this case. So 2. Oh no, actually, 2x is just a constant. 2x is just a constant. So it's 2xy.
Yeah, so
Because
would you just have a 2 there? Like, I don't know, because for some reason I just feel like I did some kind of form of derivatives where you would
it's
almost do
actually
it the same
2x.
way, but you would swap the variables at the end.
Don't do that. The very, like, when you're trying to add or multiply them, like the way I usually do it, and this is the way you should be doing it, is just operate on them separately, like this, so that
Mhm.
you're not swapping any variables. Like when you're doing this thing, this one is 0, right? And then when
Yeah.
you do this dy, that's just 1.
Hmm.
And then if you did like maybe like x y, and then let's talk about like maybe if it's a dx of xy. So in this case, y, like, x is the constant and y is the variable, and you take the dy of xy, it'll just be x, right? And then when you take ddx of xy, it'll just be y. because x is not raised to a power.
Mhm.
And maybe we'll do more of this, d dy of like, let's say y, xy squared. What is the partial of that?
Then it
It's
would just be 2y.
this guy. So since x is just a constant, so it's 2y, right?
Yeah, so it'd just be
2xy.
2y
Yeah.
x.
And what about ddx of x squared y squared?
Yeah, you would have
Y squared is a constant,
y squared 2x.
so y squared, and this is 2x, right? So
Right.
2x y squared. Okay,
Okay.
that one makes sense. If it's like being added, it's being added, ddx of x plus y. You operate by just distributing it, ddx of x plus ddx of y. So
Okay.
ddx is 1, right? And this is 0, right? Okay.
Yeah.
Yeah, it's yeah, sometimes yeah, that happens. Like yeah. So yeah, for this one it's -1, and then what is this one? The partial of ddx 2y minus x.
So 2y minus x, that would be, it would just be 2.
The minus x, the 2y is it disappears, right? The 2y
Oh,
disappears.
okay. I was thinking it was dy. But anyway,
If
okay.
it's dy, it will be 2, yeah.
Okay, so 2, so it's going to be d dx of 2y minus x. That would be -1.
-1, yeah. Yeah, just if you have to review the partials, yeah, just do some of those.
Okay, so then in that case, we would get -1s for both of these.
Yeah, and then like this is the easy case. There's maybe it could be a variable, maybe it's not a constant. If it's the same variable,
Yeah, and
then
then these are equivalent, so this would
that
be
means
a
yeah.
exact.
And that's how you classify an exact. This is probably the other weird one, because then you have to do an extra step. For the integrable, y prime equals f of x. For separable, y prime equals f of x times g of y. For Bernoulli, it's y prime plus f of x times y equals g of x, y to the n. For exact, it's m partial x y times dx plus m partial y xy times dy equals 0. And you have to check if the partial of mx sub y equals the partial of ny of x
Okay.
is equivalent.
But in general, you would do this once you determine they are exact, you would pretty much treat them the same way as a separable.
Let's talk about that. So how do you solve a exact equation, right? Let's talk about how you solve for them, because it's not weird, but there is a since they're equivalent. So remember this thing. I mean, you could technically consider them as like separable, but this is usually the algorithm for it.
Okay.
Is you take. I mean, I'll pick one. I usually pick the m of x first, and then let me take the integral of that. Let me take the integral of the term in front of the dx. So m partial dx times dx, the integral, and then you make that like let me see, and then you make that equal, so that right there, the 2 of x minus y dx, then you have an integral. Just evaluate that, and you should get to you have x squared minus y of x, right?
Squared
Minus y of x.
minus y of x.
Does that
Okay.
make sense? Does that not make
Yeah.
sense? And then the thing is,
Okay.
this is multivariate, right? This is like x and y.
Yeah.
So since it's multivariate, you can't just add in like a constant, right? Like you have to add in the a function of y. Do you remember that in calculus 3?
Yeah, hold on. I'm just trying to kind of solve
Okay.
this
Okay.
equation. So you would have you could pull out the 2, and then you would have an x squared over 2. That cancels to just get x squared. Okay, and
Okay.
then the y dx becomes yx dx. Okay.
Okay.
Yeah.
Okay. And then do you have, so the constant of integration, since you have a y here, you have to account for that, right?
Y is your constant of integration?
Yeah, it's not going to be a constant. It's going to be a function of y, right?
I don't understand what you mean. So why is y the constant of integration?
Because your m of x is a function of x and y, right?
So m of x is the function of x and y.
Yeah. And then if you remember doing that, if you take an integral of like a multivariate function, and you're only taking the integral of it with one, keeping the other one constant, your constant of integration is not going to be it's not going to be a constant. It's going to be a function of your other variable that you've stayed a fix.
Okay, so since it's m partial x, the other variable here would be our constant of integration.
Yeah, a function of that guy.
So it'd be f of y.
It could be f of y, g of y. It doesn't matter. It could be a function of y. It could be f of y. Yeah, let's make it f of y.
Okay, so this would be f of y equals 2x minus y.
It wouldn't be equal. So this whole thing right here, this is where after you do that, after you do the integral. So this, if you've seen this before, this whole thing is fx of y, right?
Mm-hmm.
And like this is just what you have right here. So df equals m of x times d of x. The total integral is n of y times d of y, right? The total integral of df, the total differential of df is m sub x times d of x plus n sub y times d of y, right? And then when you take the integral, when you take the integral of that, you have f of x of y equals, this is kind of like, m x dx plus n y dy, right? And then
X dx.
yeah. And then this whole thing was equal 0, right? Wasn't this whole thing equal 0?
So let's see, mx dx plus ny dy equals 0.
Right? This whole thing was equal 0, right?
Yeah, that was the
So
form.
so if you take an integral of 0, what is that?
Integral of 0 is just
Constant, right?
x.
It's a constant,
Oh,
right?
it's just c?
Yeah. So this whole thing equals c once you take the integral.
Wait,
Okay.
integral of just 0 or integral of the left and the right?
No, like it's just the right. The right hand side is 0. We still have to evaluate these. We have already evaluated one of them, but the right hand side, which was 0, when you take the integral of that, it's just going to be
Okay.
c. It's just going to be c, right?
Yeah.
Constant of integration. So that's where your constant of integration pops out.
Okay.
Okay. So with that process, let me just delete this one. So with that process, since you have this g of y, and then you did take this, making it equal f of x. Now let's take a partial of like this guy, the f of xy. A partial with respect to y. So when we took the partial with respect to y, that was just the ny term, right? Wasn't that just the ny term?
d to y of, yeah,
Because
your dy
when you
would
take a
be n.
partial of like your total with respect to dx, that was the m of x. But when you take a partial with respect to y, that was your n of y.
Okay, I kind of got lost there. So
Okay,
d dy
so you have
f of
m of
x.
x dx plus n of y dy, right? Equals
Right.
0. But this whole thing is, well, what is this whole thing? This is d of f of x of y, right?
F of f df of x.
Right. This is a total derivative.
Okay, so in the original equation definition, you would have df of xy.
Yeah, I just didn't define it that way, but that is what it is. I
Okay.
just didn't like in the original equation. It's just this guy. But if you think about it, this guy is just a total derivative. By definition, what is a total derivative? It's the partial of. And then let's just say that we're not using m, but let's use f. Maybe that will make more sense if you use f, right? Sometimes people use f. Sometimes people use m and n. Does this make sense now? The total derivative of f, because it's a multivariate, is a partial derivative of f with respect to x times d of x
Okay. Yeah.
times the partial derivative of f with respect to y times d of y. That makes sense, right?
Hmm.
Sometimes people use f, sometimes people use m and n. Play your game. Just make sure that you know what a total derivative is. So if you know that, and then this right here, this term right here, right? This term right here, the d dy of f, is just n of y, right?
d dy. Okay, hold on. I'm just trying to
Uh,
write this all down.
Okay.
Okay, so df is d partial, I guess, partial
dy,
d
partial
with,
dy.
yeah, partial dx
Let me rewrite this
of
down.
f x y dx plus d dy of f y x y dy, and then, yeah, okay.
You got it?
Yeah.
Okay. So with that, you take the partial, you make it equal to ny, which is what the definition is. And then since you take the partial of like this df, we already know that the partial of the df is also a constant because this is the right hand side.
Okay.
And so we already found what f of x y was, right? We already found that one out.
f of x y.
Is what we got right here.
Hmm. So what? Okay, so what is our f x y?
So your f of xy is this whole thing right here. But what you have to do, this is like I said, don't get bogged down. What you have to do first is when you take the integral of your m sub x, the term in front of the dx, you make that equal this guy, the f of xy.
So you set the mx dx to equal the dy?
The not the dy, the f of xy, f of xy.
f of xy.
Yeah, the the integral of your m of x dx is going to equal your f
Integral.
of xy.
I'm confused.
Yeah, I know. Like I said, this exact equation is a little weird. And also with the Bernoulli. If you guys will have it, you probably have to do it many times. But let me see if you can. Let me put it right here. So the very first thing you have to do, and this is finding the general solution to a exact equation. So you know how like you have this m of x, right? Right? You have this guy.
Okay.
plus like n of y dy equals 0, right?
Mm-hmm.
In order to find a general solution, the very first thing you do is this. Maybe I can make it equal f of x. Let's just not, because that's confusing you. Let's take the integral of mx dx, right?
Okay.
Let's do that. After you do that, you put that back in here. But then now you take the result of that, you put it as a partial d dy.
Okay, so do you solve the integral first?
You solve the integral first, yeah. I'm just talking in like generality here. So that so we know where the terms are coming from. So so this whole thing, you do that next. The second thing is you do this. You solve for the integral first, and then you put it right here. You take partial d dy, and you make it equal ny. And
Okay, so you just do one integration and then you do a derivative twice?
you do you take the integral of this guy, right? And you're gonna get something, maybe like x terms, some x terms plus like a g of y. That's usually what it is. So some x terms times like a g plus a g of y. You put that in here because this is multivariate, and then you take the dd of y.
So what does the g of y look like? So,
You're gonna end up solving for the g of y. This is the complicated part. Yeah. Right now it's arbitrary, a constant. I mean, it's not a constant, but it's an integration term that came out of the integration of this guy. And the reason why it came out because you were only taking an integral with respect to x. So you have to account for the other variable, which is y. And then after you get that, you have to take the partial of d dy. This is partial d dy, not d dx. So it's fine to do that, right? It's not going to go to 0, right? It's if I were to take the partial of x plus g of y, what is the answer there? You distribute this guy, right?
I don't know.
These partials are a little bit hard to
Okay.
grasp, but it doesn't go to 0. You have to follow the rules.
Okay, I just don't understand how when you do the very first step, when you integrate, why you get a function.
It's calculus 3. Do you remember calculus 3 with multivariate?
No, not really.
It's because you have multivariate. You're not taking when you create. It's like a rule. For example, if I did just this, it's just a function of x only, right?
Mm-hmm.
So if I did that, it would be like what, x squared over 2 plus c, right?
Right.
Where c is a constant. But then like, what if it's a multivariate function? What if it's a multivariate and I'm only taking in terms of x? What this is going to be f prime f. Let me see. It would be this guy. Let's do this in terms of, where you actually put like 2x, maybe like y dx. It's not going to be a constant because you have a y here. So if you do this, the y is constant. So you have this guy and then the 2. So you're only taking a derivative of this guy actually, or like integral. So x squared over 2y. And then you have to account for the one that you didn't take an integral of. So what you're going to pop out is a function of y. So x squared y plus g of y. The other thing, if it was in terms of,
So it's not plus c?
it's not plus c. It'll never be plus c. So what if it's like a d dy? What if this is a d dy? It's going to be 2 of x y dy, 2 of x y squared over 2. And it's not going to be in terms of y now. It's going to be in terms of x. Because this thing is the one that we're taking an integral of.
So dy becomes gx.
It doesn't become it. It the integration term that pops out is just a function of what your other term is. Just think about it that way. Like if your function inside your integrand is a function of both x and y, and you're only taking an integral with respect to one of them, the constant that pops out because of your integration is just going to be a function of the one that you kept a fix. So if you're taking an integral with respect to x, the function is going to be is y.
So you're saying you pull out the g of y?
This is what you're going to solve for. Yeah, you're going to solve for this after.
I don't know.
Yep, this is calculus 3. Yeah, that's why this thing is that the exact one is a little bit weird again. Bernoulli is not that much, but so like knowing that, since you have a g of y now, this x squared minus y of x plus g of y, you take a partial derivative, right, with respect to y. That's what you have to do. And you make it equal n of y.
N of y.
And then you know n of y.
N of y. So we would just plug an n of y in there?
Yeah. And then the harder part is doing the d dy of this guy. So doing the d dy of whatever you just solved for, right? This guy.
I mean, since we end up, when we take the derivative and we always get the n of y, do you even have to do any work there, or can you just replace your derivative with your n?
You can't. This is not how that works. It's what we're gonna do right now is we have to solve for the g of y. Remember, we still have this g of y term.
Right?
Yeah. So
Yes.
since you have this g of y term, you're gonna make it equal to this n of y. And then let's try to actually do something to this guy. So what is the d dy of this guy?
Do I?
So the x squared goes to 0, right?
Yeah, and then you would get x,
Minus x.
just minus x.
Yep. And then what about g of y? What is the d dy of that?
Y? Or
It's a
just one?
function. It's a function, right?
G of y. I mean, we don't know what g of y is.
You don't, so keep it arbitrary. So what is the derivative of a function? G prime, right? Of y. Or f prime of y, whatever. Keep it arbitrary for now, because you're going to solve for it.
Okay.
Okay, so g prime of y, and then let's simplify it. So it's minus x plus g prime. It's a function of y, and then let's plug in what ny was. What was it? 2y minus x, right?
1 minus x.
Okay, so this is kind of separable, isn't it?
I guess
Like,
so.
and like, what can you do with the x's? Or like, it can be integrable in a way. Let's make it integral. What happens with the x's?
So you would bring them over to the other side and
But they cancel out, right?
yeah.
So since they cancel out, you're gonna have g prime of y equals 2y. This is integrable now. Okay. So what do you do with the sum?
You would just replace it.
You would take the integral, right? Try
Okay,
like
take the integral then.
because you want the goal is to get g of y, right? Take the integral with respect to d of y, with respect to y.
Okay.
So you get g of y equals the integral of 2 of y dy. What is that?
So that would just be y squared.
Yeah, that would be y squared. Yeah, y squared. So what did we accomplish? We got g of y now, right?
Okay.
And then that's why you do that, because you have to solve for it.
Okay, so after we get g of y, what is
What's
done
next? What's
next?
Okay, so with all of that said, you plug it back into where it was, like right here. So this is me writing it: x squared minus y of x, and then plus g of y, but then that's y squared, so plus y squared.
Okay.
And this right here is your f of x, as we said. This is actually what you're solving for. The general equation is a solution. It's going to be a function of x and y, which is what it is, right? It's a function of x and y. And don't forget that this whole thing equals c, because the right hand side is 0, and then the integral of 0 is just a constant, which is c. So this is your general solution. Kind of weird, but this is the exact solution. The exact equation gives you a general solution that's like an fx of y.
Okay, so how do you know, like, what exactly is a general solution?
A general solution is one with a constant right here.
Okay.
That you have to plug in the initial condition to solve for, and that's what we're going to do next to get a particular solution. A general solution is like something that has like a constant in there that you have to solve for.
Okay.
And you make it specific, you make it unique by applying the initial condition. So it's a little like, how did we apply the initial condition to a differential equation? How did we do that? Like for a regular equation, how did you do that?
So you plug in your x and your y's.
Yeah, but then like
And
usually
solve for c, and then
yeah,
you would plug that c back into your general solution to get your answer.
exactly. That's good. But then like, if you look at this is not in terms of y, right? Like
It
this whole
is.
thing, it's like an fx of y. It's like a bunch of x and y's, like an expression of it.
Yeah.
I mean,
So
it still is. So like I'm just saying, like if you're given like this guy, then you can translate it as like x equals 1 and then y equals 3, right?
yeah.
Yeah. Okay. So yeah, if you got that, that's good. So, and all you have to do is plug in the x equals 1 and then y equals 3, and then solve for c, which is 7. And then this is your unique solution. But I think you can still go so far, go an extra step. I don't know if we should cover it, but do you want to see what it is?
I guess so, yeah. So
Okay. So you have this like a bunch of things that's not y isn't isolated, right? So, but like, look at this. What's something that you can maybe adapt or like remember that you've done before to solve for y and make it in terms of x? What did you do in like maybe algebra 2 or 1?
so I mean,
How did you solve for y in terms of like an x given a polynomial?
you would use the quadratic formula.
Yep. You would use the quadratic formula, and that's what you have to do in this case. If it's like a y squared, if it's not a y squared, then you have to do other things. So you pretty much use this and then convert it to the form of the quadratic equation formula. So you have like a equals 1 B and C. Apply this. And I'm not gonna go over like how you do that, but like obviously they're not numbers, they're variables, B and C. And then you simplify everything and you should get your final Y, which is what you've been looking for, a Y of X, right?
Right.
And that's how you get it in terms of Y of X, using the quadratic formula.
Okay.
Does that make sense? Kind of.
Yeah, kind of.
Okay. So that's pretty much like those. I really want to cover like these, like the inhomogeneous ones. Remember reduction of order?
Yeah, reduction of order.
This is actually in like, there's like I didn't really cover this part, but maybe I don't wanna. The thing is, it's in your review. Did you touch on this one yet? The one where you applied the reduction of order?
Reduction of order. Not yet.
Okay, I'll just cover this part because like the reduction of order. When did we apply that? When you had variable coefficients, right? Variable coefficients. So like when you had like t squared y prime plus,
Yeah.
or like this guy, right? Y prime plus like y equals t squared, or equals 0 rather. When your coefficients were variable.
Yes.
But in actuality, like that's it's actually more than that. It's like a general equation. So like I don't know why your professor is showing that, because for the most part we don't really apply it when there's constant coefficients. But just remember, like, this is the equation. It's a little weird. I don't know why he covers it that way. Because like the review actually goes over this. So if you remember, for the reduction of order, you're usually given the y1. Yeah.
Y1.
Besides the differential equation, you have to be given the one of the terms of your general solution.
Okay.
You have to be given that guy, the y1. And then so if you look at this, you're probably wondering, why do we need to apply the reduction of orders? We don't have variable coefficients. We have constant coefficients. We could
Okay,
just
so is
yeah.
is this form that you boxed, is that the form of the, like the top box?
Yeah.
Is that the form of reduction of order, or is that just an example where you would use the reduction of order?
So this, oh yeah, let me explain it. So this y2 is how you apply it. So you use the reduction of order by taking your y1 that's given to you, and this is only for a constant coefficient.
Okay.
Your professor uses it this way. He uses this equation.
Okay, so you would have to integrating factor over your y1 squared.
Yeah, and it's just an equation that I guess he wants you guys to apply when you have constant coefficients and you're using reduction of orders. And then the main point is, given y1, you need to get y2. Y2 is the second fundamental solution to your general to your differential equation. So let's actually go over like how you use this. So the very first step is given the differential equation, and then the one of the fundamental solutions. You need to find the y2, the second fundamental solution. So okay, so you have y2 equals, this equation, right?
X dx. Okay, so that's going to be over y1 squared.
Yeah.
Okay, so you're given
What
the
is y1?
differential equation.
And then this p of x, I forgot to say, the this p of x in this case, it's not the term in front of the y, it's the term in front of the y prime. In this case is the term in front of the y prime.
Wait, what? Okay. Y double prime
You
minus
don't have a
4y.
y prime, right?
Yeah, your y prime 0.
So this guy right here is 0, so it's e to the power of 0, which is 1.
Okay.
So simple. And then just plug in the y1s. So e to the negative 2x, e to the negative 4x.
So px dx is your first derivative?
Is the first derivative, yeah, the y prime. Only in this case, in the regular integrating factor, it's the term in the what? It's the term in the integrating factor way, the first order. The p of x is the term in front of your y, right? Not your y prime.
In front of your y.
That's for your first order. In this case, we're using reduction of orders. You have to use it's the p of x is the term in front of your y prime. Only in this case. Only in this case.
Okay.
Okay.
I guess so.
Okay, let's breeze through it because I wanted to cover the undetermined and the variation of parameters. Okay, so after you do that, 1 over this guy, and then you have you do the integral. Integral of this is just 1/4 over e to the 4x, right? And then so e to the 2x, and then this thing is 1/4, but the thing is what you want to actually get is the fundamental solution. So it doesn't matter what your constant in front of this guy, like 1/4 e to the 2x. This constant is just gonna get lumped into an arbitrary constant, which is this guy right here, c2 e to the 2x. And that's it. That's how you get your y2. The reason why I have this equation, and your professor wants you to use it, is given y1, you can get the y2. Okay. So in terms of general solution, the only thing you have to do is the y equals c1 y1 plus c2 y2.
C1, y1, C2, y2.
Yeah, or maybe y1 actually. Y1, whatever it is, you're given the y1 itself, but you always have to put in the arbitrary constant. You're given the fundamental, and you always put the c2, and this should look familiar to you, right? c1e to the -2, and then c2e to the 2, right?
Yeah. Would you do like a Ronskin here?
Not in this case because we're not doing the particular solution.
Oh, okay. We're not, because those find particular solutions, right?
Yeah, but not the particular in a non-homogeneous. This is for a homogeneous case. That's why I didn't want to use that term. Unique solution. We're trying to find a unique solution, yeah. Because this is a homogeneous one, right? Yeah. So after you do that, I'll skip this step because you already know how to do this part. Okay, let's go to, do you remember doing undetermined coefficients? We'll just kind of breeze through it. But we kind of did this twice.
Okay.
So undetermined coefficient, when you apply it is when you have an inhomogeneous case, right? Because you need this to find the particular and the complementary, right?
Okay.
So the undetermined coefficient, it helps you find the yp. And then the y complementary comes from this side, right? It comes from this this characteristic equation that you have to solve for. Okay. So given this inhomogeneous equation, the very first step is to find what?
Your
complementary or homogeneous solution.
Okay. So you would basically have to make those in terms of x instead of y. Because
for which one?
we already have the complementary here.
For which one?
It's on the left side of the equation. That's your complementary, right?
It's not. It's a differential equation. You have to solve for the complementary, right?
Okay, so yeah, because I was just wondering because you circled the left side and wrote YC.
Oh no. That what I'm trying to do here is this is where you get the complementary.
Okay, so you would
Yeah,
solve for it.
it's just like connecting the terms.
Okay.
Like you have to solve something here to get the YC. You have to do something here to get the YP.
Okay.
Maybe I shouldn't do that, but like what I'm trying to say there is.
No, I understand.
Yeah. Okay. So the YC is. Do you remember doing the YC for undetermined coefficients?
Um, Not so much. Would you
Okay.
use you would basically make the general solution of it. So you would
Yeah.
change that into K's.
K's, R's, whatever you want.
Okay.
You just need to form a
Lambdas.
or lambdas. You can just form a characteristic equation,
Okay.
and then from that auxiliary or whatever your characteristic, you get your K's. Okay. So whatever the roots of your characteristic equation are. Do you remember doing that? The distinct real
Yeah,
roots.
or distinct real.
Yeah. So because you have distinct real roots, this is your solution. E to the minus 2t, e to the 6t, plus the constants, or like the constants multiplied by them.
Yeah.
So that's how you do that. And then the next step, this is the part where it's different for the undetermined and then the variation of parameters. You use Wronskian for variation. You don't use Wronskian for undetermined. What you do for the undetermined is you have to find the counterparts. Let me say that. Like you have to find the differential degrees of the YP. And then the YP, how do you find YP though for undetermined?
YP.
It depends on the right hand side, right?
Yes, I guess so.
It depends on the right hand side. So do you remember that table we talked about?
Yes.
So since your right hand side is a exponential term with
So
a constant, what does your YP look like?
that would be the AE to the KT or BT or
5t?
well, it's just 5T.
You have to match what this guy is. Okay, but I don't want to use A in this case. It's up to you if you want to use A. I want to use C3 just to like continue what I have here.
Okay.
So I use C3 e to the 5t. And then you find the y prime t and y double prime of p. And that's pretty much straightforward. And then what's the next thing?
Okay.
What's the next thing you do?
I mean, you would solve for the other piece, I think.
And then so you plug in the yp, y prime of p, and then y double prime of p back to the differential equation, right? Like your differential equation was y prime minus 4y prime minus 12y
Okay.
equals 3e to the 5t. Yeah?
3 and
Where
5T.
where you see the y, you put in the p, because
Yeah.
the particle solution is just a solution to your differential equation, right?
Mm-hmm.
So it should work. And so this is what I have here. And
Okay.
the main point of why you're doing this is you're solving for C3, the particular solution constant, the C3. Don't forget that one. Why are you doing this? You have to solve for C3 or A, whatever you want to put. Yeah?
So you would do C3.
You're solving for that.
Okay.
Like
Do you like set both sides to have the same variables, and you would solve for each of those pieces?
yeah, so it's kind of similar to what we did before. Like, so you plug in the y double prime, right? This is y double prime minus 4y prime minus 12y p, or like y, just yp itself. These are yp's.
Okay.
And then simplify. After you simplify this whole thing, they're pretty much like terms, right? Look at them. This is an easy one. So I would just factor out the like term and then do the arithmetic. and then simplify the arithmetic, minus 7c3. And look at this. It's pretty much the same, right? E to the 5t on both sides.
Yeah.
So you make them equal each other because they're the same like term. You equivalize, you make it equivalent like terms. And the coefficients should be the same if they have to be the same. So you just operate on the coefficients of those guys. And then, so then that's how you solve for C3. That's pretty straightforward, right?
Yeah.
Okay. And after that, you plug in back to the YP equation. So you have your YC, and now you have your YP. What's next?
You would add them together?
Yeah, you add them together to get the total solution. That's it. This is an easy one. I think this makes more sense than the variation of parameters. Okay, let's cover the last one. Variation of parameters. This is like a really, I mean, I like it, but only certain equations. Okay, so this is the one. The ROO is reduction of orders, and VOP is variation of parameters. So let's take a look at this. Ask me anything about this. I don't mind going overtime because this one is kind of like hard.
Okay. Yeah,
so,
I feel like I would have questions, but I don't know. I don't know if I can think well because it's just late.
okay. Let's just cover it, and then you do have this though, right? This is the last one on that list of things I sent.
Yes.
Okay. But when you look at this, the reason why you apply the reduction of orders and then the variation of parameters is, when do you apply the reduction of orders? When do you apply that?
Reduction of order. I don't know, when you have a second order.
What kind of second order? Remember, there's the constant coefficient and then the variable coefficient.
You have a squared.
No, the reduction of orders is when these guys are variable. These guys are variable.
Okay, variable coefficients.
Yeah, that's when you apply the reduction of orders. But your professor wants you to apply them as well when you have constant. I don't know why.
Okay.
Don't get confused with that, because the reduction of orders is only applied when you have a variable coefficient in front of your y's. And so what about the variation of parameters? When do you apply that?
When you, I don't know, when you have a non-zero.
Yes. When you have a non-homogeneous, right, or inhomogeneous.
Okay, do you just do that? Do you just apply that on the right?
In essence, no. That's how you recognize that you have to do it. Like, the reason why you know that you have to apply it is you have to look at your right-hand side. This is what I'm saying here. So since this is non-zero, it's non-zero, that's why you have to apply your VOP.
Okay.
Part of the doing all these algorithms and knowing them is knowing when and when not to apply them. So the VOP is applied by looking at the right-hand side. If it's non-zero, then it's VOP to go. The ROO, the reduction of orders, is applied when you look at the left-hand side, and then you assess, do I have variable coefficients? If you do, then you apply the reduction of orders. Okay. Let me just take those out so to make things clearer. Okay, so same thing. Let's find the general solution. I don't feel like doing the particular one. So with the reduction of orders, what do you have to be given?
So for reduction,
You have to be given something, right?
order, you should be given your y1.
Exactly. Good. You're given your y1. So the one thing that you want to do here is, I want to find the yc. And because this is inhomogeneous, right?
Okay, you use your y1. When you have y1, you know you have to do reduction of order?
Yes. You could say that, yeah. And then but then this is inhomogeneous, right? So that means that we need to find the yc, right?
Non-homogeneous, okay.
But you need to find the YC, right?
Find YC. Okay.
I want you to connect these two because this is like the final destination is when of like this first part of like differential equations is when you have the ultimate like equation where you have them like non-zero, you have variable coefficients, then you need to apply the reduction of orders. But in this case, before we only use reduction of orders to get the y2, but in actuality, we get the since we're already given y1.
Okay, we're given y1.
We can just get the complementary solution, right? And what is the complementary solution? C1 times y1 plus C2 times y2, right?
Okay. C1 y1 plus C2 y2 is yc.
That's your complementary solution, right? And then this y1 is given to you. Now, the very first thing you have to do now is to solve for y2 first.
Okay.
Okay, just accept that, and then we'll kind of unpack it. So what we have to do is you have to make, since you're given y1, you have to make y2 in terms of like y1 times a variable. So the variable I chose is u times y1 equals y2.
I don't know why it's not making sense.
Yeah, I know this is just an algorithm. It's I think you got to do more of it. Like it's just an algorithm, let's say. So when you do that one, y2 equals u times y1. And then so the reason why we do this is so there's no, there's no way you can solve for y2. So why not we just make it equal y1 somehow? So this u times this t minus to the negative 1, that's y1, right? Isn't that y1?
Y1. How is t y1?
We gave that in the problem. We gave it
I
right
thought
here.
t to the like 1 over 2 was y1.
1 over 2, yeah. It's exactly the same. T to the negative 1. Right here,
Okay.
t to the negative 1.
Okay, for some reason I thought you said t was y1.
No, t to the negative 1.
Okay.
Okay. So when you do that, you plug it in right here, right? You plug it in right here.
Okay.
Okay, and then so the one thing you gotta do after you do that, it's kind of similar to the undetermined coefficient, is so now that you have a y2, you have to find its derivatives. So find its derivatives because you're given this u times t to the negative 1.
Okay. Is it just because I don't really know how you got the u y1 as being y2? Is that just the formula?
It's a formula that you have to do when you're applying reduction of orders. It's
Okay.
a cookbook. This is what you have to just do.
So y2 is u y1.
And then
Okay.
eventually this u, you're going to have to solve or do something with this u. And that's why we're doing it this way. So so if you do this, you solve for the, you're trying to get the derivatives. So you do this, right? So you get the derivatives, use product rule. And then what's next?
y2. Okay, so you just took two derivatives. Okay, and then from here.
From here, remember what we did with undetermined? You look at your differential equation. You look at your differential equation.
Okay, and you replace y with yp?
With y2, in this case, yeah.
Y2.
In this case, it's y2. They're kind of similar, but it's y2. So plug and chug. And then after you do that, you know, this is just plugging and chugging right here. You can do this later. It just simplifies. It pretty much simplifies to a very easy equation, which is this guy right here. After you plug it in right here, all this is just like algebra so that I can get to this point.
Okay.
And then this part is going to sound like weird, but the thing is, this is the reason why it's called reduction of orders. The reason why it's called reduction of orders is, so you see this u right here? You see this u?
Mm-hmm. Becomes a v.
So this u is a second order, right?
Mm-hmm.
And then this u is a first order, right?
Yeah.
So we're using reduction of orders so that we don't have to solve a second order differential equation. I wanna replace the u double prime with a v one prime, and then the u one prime into a v. So now I want to substitute for those guys. That's why it's a reduction of order. So wherever you see a u, substitute a v. So now it's this guy to the first power, to the first derivative. And then look at this. Your second order differential equation became a first order. It was a second order, and now it's a first order.
Okay.
So, do you know how to solve a first order?
I mean, not really. 2t.
In the integrating factor, right?
Oh yeah, integrating factor.
That's like the only way. I mean, not only, but the easiest way. So that's what you have to apply. Solve for this. Now you don't have to solve and apply all those like weird the second order tactics. You can just use integrating factor. So you find your, obviously you applying the integrating factor. I'm not gonna explain it, but you want to make your term in front of the first derivative to be 1.
Right.
So you divide it by whatever's in front of it, and then whatever's in front of the 0th derivative, that's your PT. This is PT. This is PT. Because the integrating factor is just e to the negative to the integral of PT, right?
PT dt. Yeah.
Yeah. So this one makes sense. The other one, the exact, I think, or the other one doesn't make sense. But in this case, this is what you do. And then you just do some algebra, and you get that the integrating factor is this guy.
Okay.
After you do that, you times it. You times your integrating factor to your whole first order differential equation. You have this v prime equals 3 divided by 2t times v equals 0, right?
Yeah.
And then so I distribute that guy. And then what was it? What was the thing that you have to find? A reverse product rule, right?
Right.
So the reverse product rule that I found here is t to the negative 3 over 2 times v, all of that quantity prime. So that's the product rule.
Yeah.
So after that, I would just take the integral of both sides. And then so this is already a derivative, so I'll just take whatever's inside. And then what's the integral of 0?
C.
C. And then so you isolate that guy. And then you isolate the v. And then you get v equals c, t to the 3 over 2.
Over 2.
So this is your answer to the v, right? This is the general solution to the v, right?
Right.
But is that what we want? Is that what we want?
No, we want u.
You want u. So what was v?
V was u prime.
U prime. So you plug u prime back in, and then you do more integrals. So more integral, you want u now. And then this is the part where it's a little weird, but it's up to the mathematician or like the physicist, whatever. So like you have this guy, right? This integral of, like you have this, after you do the integral, you have c 2/5 times t to the 5 halves plus some arbitrary constant, right?
Yeah.
For the reduction of orders, what you want is you make the arbitrary constants to be 0. And then the C, the C that you found from like the V, you have the C right here. You make this so that you can cancel out your coefficient. So since our coefficient is 2/5, I'm going to make the C 5/2. And in the end, no rhyme and reason why, but what you want to do is you just want this guy to be isolated. You want the two, what's it called? You want the T to the 5/2. That's all you want. You don't want any C's, you don't want any K's in there.
Yeah.
Okay, so now you have the U, right? This is what you want, right? The U. And then you also have the Y1, right? That was given to you. So
Yeah.
what's the next step?
You just plug back everything.
To the Y2, right?
Oh, into the Y2. Okay.
Yeah, because what was Y2? Y2 is U times Y1, right? That's what we made it as, because you're applying reduction of orders. You have to do it that way.
Yeah.
So you do that, and then you get that Y2 is T to the 3/2. So now we have Y2 and Y1. Y2 and Y1. What's the next thing?
So you have your original function,
So
and
now you can create the complementary solution, right?
yeah. So let's see, 1y1 plus
Y2.
c2y2.
Yeah, this guy, plug in everything you get, from what you know to this guy. So that's YC. So that was only 1/2 of the thing, actually. That was only reduction of orders.
Yeah.
Does that at least make sense, the reduction of orders?
Kind of. It's a lot.
I know, but then the next thing is, I'll just brief it. It's a variation of parameters. Do you remember doing this? This is the one with the Wronskian.
Yeah. That's with a non-homogeneous.
Yeah, so this is a 2x2, so this is an easy one. So what was the first thing you had to do? You had to get your Y1 and Y2s, right?
Right.
And see how it connects now? You got Y1, it was given to you. You were solving for Y2 using reduction of parameters, right?
Mm-hmm.
And then you already have a right-hand side, right?
Yeah.
You have a right-hand side because it's inhomogeneous, non-zero. So what do you do? What's the only missing thing? The Wronskian. Right?
Okay. Yeah.
And then the Wronskian, you apply it, just take the determinant of a 2x2. And then I'll just skip the math, linear algebra stuff. You just do this, you get the Wronskian. Good. And then you apply the equation for variation of parameters for a 2x2. Which is yp equals minus y1, the integral of y2 times the r of t over the Wronskian dt, plus y2, the integral of y1 times the r of t over the Wronskian dt. Do you remember that one?
dt. Yeah.
Okay.
Okay. So,
And now just plug and chug, right?
mm-hmm.
But then plug and chug until you have to take an integral.
Yeah, because you gotta just have the t by itself because it's probably not in the right power, or it's not I don't know the word, it's not zeroth order.
Yeah, not zeroth order, yeah. But then in the end, all that math will just give you the yp, right?
The yp.
That's the reason why you're doing the variation of parameters to get the yp.
Get yp at the end.
Yeah. And then the reduction of orders, what did you get in the end? The yc.
Yc.
Yeah. So you have yp from the VOP and the yc from the ROO. What's the last thing?
You just plug everything in.
Yep. So the total solution, general solution, is yp equals yc of t plus yp of t. Plug, plug, plug. And this is still general because you have the C1s and C2s, right?
C1s and C2s.
From the complementary solution. So if you plug in an initial condition to solve for C1 and C2, you should get the unique solution. Yeah?
Okay.
That's like pretty much a whirlwind of like what you might see.
Mm-hmm.
Okay, man. Yeah, I think that was good. Let me know if you need like I guess another tip tomorrow. If there's anything you get stuck on, I can just
Okay.
send you something.
Yeah, I'll do that.
Okay. All right. Have a good night, and then like please let me know how you do. And then we'll
Okay.
meet again on Sunday. We're gonna meet again on Sunday. So
Yes.
cool. Oh yeah. Send me what things do you have for Sunday?
Okay. Sunday, there's nothing due for math on Sunday.
Oh, nice. That's good.
Yeah, I do have some questions on the T10, I believe, or I don't remember if it's T10 or T11. I don't know, but I have some questions on the PChem stuff. I'll have to look for it this weekend, and I'll let you know.
Okay. So Cam something T10, right?
Yeah, it's T10. It's either T10, T11, or T12, but I'll have to send you that new material.
Okay. So all of Sundays we're gonna talk about Cam.
Yeah,
Okay.
pretty much.
All right. And then like let me know if you guys will do Laplace transforms or some like word problem. I don't know if you guys are gonna move on to the word problem for like this class.
Okay, yeah, because I know every one of these math classes is gonna have like a word problem section.
Yeah, like this guy. It was all math but no physics. Okay, cool. Have a good
Okay.
one.
Yep.
All right.